Welcome to the Explainer. Today, we're taking a high-stakes, no-nonsense journey into spatial geometry. If you want to absolutely dominate your Cambridge mathematics exams, you need to completely master the foundational rules of symmetry. Listen, when the exam pushes you out of your comfort zone, you have to push back, with perfect, bulletproof answers. Whether you realize it or not, symmetry governs the design of literally everything around us. By the end of our session today, you won't just see simple shapes. You're going to instantly recognize the hidden mathematical frameworks that hold them together, and you're going to know exactly how to extract marks from them. Let's get to work. I want you to start by doing a little mental geometry with me right now. Imagine holding a perfectly carved wooden block in your hands. Can you picture the exact invisible planes you'd need to slice right through it so that both halves are perfect mirror images? You know, it's pretty easy to think about folding a flat piece of paper, but mapping that exact same logic onto a three-dimensional solid, that takes a specific, elite kind of spatial reasoning. And that mental leap is exactly what we are going to conquer today. Here is our game plan for today. 1. Mastering 2D line symmetry. 2. Understanding rotational symmetry. 3. Stepping into 3D space. 4. Calculating polygon angles. And 5. The ultimate symmetry summary. Let's kick things off with Section 1, Mastering 2D line symmetry. We're stripping away depth for a second to focus on the simple, powerful act of folding flat shapes.
Before we dive into the core definition, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's break this down. A line of symmetry is an invisible boundary that divides a shape into two completely identical parts so that it perfectly reflects onto itself. Think of it as a mirror placed exactly across the shape. If the reflection in the mirror perfectly completes the other half of the shape you see on the page, boom, you've found your line of symmetry. It's a precise, concrete mathematical rule grounded entirely in visual intuition.
Now, it becomes immediately clear that different shapes possess entirely different symmetry profiles. Take a look at the isosceles triangle we're showing here. You can see that single, bold line slicing straight down vertically from the top point. That's its one and only line of symmetry. If you fold it along that line, the two halves meet flawlessly. But look next to it at the rectangle. The rectangle gives us options. We can slice it vertically, or we can slice it horizontally. The rectangle has exactly two lines of symmetry.
Up until now, our brains have basically been doing one thing, folding. We've been looking at flat objects and imagining folding them over a line to see if they reflect onto themselves. But advanced geometry isn't just about static mirrors. It's about movement. To secure those top grades, we need to transition our minds from the concept of folding and reflecting to a totally different physical action, turning and spinning.
Which brings us to Section 2, Understanding Rotational Symmetry. We are no longer just folding shapes in half. We are spinning them around a fixed point.
Check out the top shape here. Looks kind of like a three-bladed propeller, right? Notice the center point marked O. If you literally pin that shape at center O and give it a spin, it will look exactly the same in three distinct positions before it completes one full 360-degree circle. Because of this, we say it has a rotational symmetry of order 3. The order is simply the exact number of times a shape fits perfectly onto its original outline in one complete turn. Now, contrast that with the arch shape beneath it. If you spin that arch, it won't look like an upright arch again until you spin it all the way around to where you started. There's only one single position where it fits the original. In mathematics, we say a shape like that has no rotational symmetry, or if you want to be super technical about it, rotational symmetry of order 1.
And this brilliantly illustrates how we can construct symmetry ourselves, a classic maneuver you need to know. Look at the grid setup. The objective is to shade 3 more squares so that the pattern has a rotational symmetry of order 2. That means if we pin it right in the exact center and rotate it 180 degrees, just a half turn, it has to look completely identical to how it started. By strategically shading those specific squares opposite the center point, we create a perfectly balanced, spinning pattern. You can literally verify these in an exam by just rotating your paper a half turn. If it matches, you've absolutely nailed the order 2 rotational symmetry.
Moving on to Section 3, Stepping into 3D space. We've mastered 2D lines and 2D spins, so now it is time to literally jump off the flat page. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @AceTheExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, when we step into 3D space, our vocabulary has to level up. A 2D flat line of symmetry evolves into a 3D plane of symmetry. Imagine taking a perfectly flat, invisible sheet of glass and sliding it straight through a 3D solid. If that glass plane divides the solid into two identical mirrored halves, you have found a plane of symmetry. It's the exact same logic as our 2D mirror, just expanded to handle depth. Let's apply this to a real 3D solid, like the cuboid we have right here. Think of it like a standard rectangular shipping box. Notice how we can slice it horizontally through the middle, vertically down the center from the front, or vertically down the center from the side. Each of those slices creates perfect mirrored halves. But it gets better. Just like 2D shapes can spin, 3D solids can rotate too. But they don't rotate around a flat dot. They rotate around a 3D axis. Imagine sliding a metal rod straight through the top of the cuboid, down through the bottom. If you spin the box on that axis, it fits onto itself twice in a full rotation, meaning it has a rotational symmetry of order 2 about that specific axis. When you map it all out, a cuboid actually has 3 of these axes of rotational symmetry.
Let's test this strategy on another shape, the square-based pyramid. Picture the Great Pyramid of Giza. Because its base is a perfect square, you can drop a plane of symmetry through it in 4 totally different ways, straight through the middle of the opposite sides and diagonally from corner to corner. But what about rotating it? If you drop a vertical axis from the very top tip straight down through the exact center of the square base, you can spin that pyramid. And because that base is a square, it's going to lock into its original footprint 4 times in one full spin. Therefore, it has one axis of rotational symmetry, and it is of order 4.
Welcome to Section 4, Calculating Polygon Angles. You might be wondering, how does this visual stuff actually help me solve hard mathematical calculations? Let's transition to the practical application. Let's dissect the problem we have here. We're asked to describe the symmetry of a regular 9-sided polygon, and then, critically, use that symmetry to find the size of each interior angle. Now remember, because the command word here implies a regular polygon, it means all sides and all angles are totally equal. Therefore, it inherently possesses 9 lines of symmetry, and it has a rotational symmetry of order 9. But how do we use that order of 9 to crack the angle calculation?
So here is the exact execution strategy. If a shape has a rotational symmetry of order 9, it means a full 360-degree rotation is divided perfectly into 9 equal turns. So step 1, we calculate the exterior angle by dividing 360 by 9. That gives us a clean exterior angle of 40 degrees. Step 2 relies on the foundational geometric fact that an exterior angle and its corresponding interior angle always sit on a straight line, meaning they add up to 180 degrees. So we simply take 180, subtract our exterior angle of 40, and boom, we have our interior angle, 140 degrees. We completely bypassed memorizing complex formulas and used pure symmetry to secure the answer. That's how you win.
Finally, Section 5, the ultimate symmetry summary. We've covered a tremendous amount of ground today, so let's lock these core geometric rules securely into your memory. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here is your ultimate cheat sheet, side by side. In 2 dimensions, we have line symmetry, where a flat figure reflects perfectly across a line. We also have 2D rotational symmetry, where a flat shape rotates perfectly about a single center point. When we level up to 3 dimensions, the framework evolves. The 2D line becomes a 3D plane of symmetry, where a solid reflects across a flat plane. And that 2D center point becomes a 3D axis, where a solid shape rotates perfectly around a central line. The fundamental logic remains exactly the same. Only the dimension changes.
As we wrap up this explainer, I want to leave you with a real challenge. You now possess a completely new lens for viewing the physical world. Geometry isn't just trapped in past papers, it's the invisible architecture of reality. Next time you pick up a coffee mug or look at a building, look past the surface. Ask yourself, where are the hidden planes? What is its axis of rotation? Apply this mental geometry everywhere. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCS to excel in your Cambridge examinations. Subscribe right now to at Ace the Exams IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.
Keep looking closely, and I'll see you in the next one.